believe we are a go for more Theano. There we go. Welcome again, everybody. Tonight we're going to keep looking at Theano, another open source machine learning framework. I'm trying to fiddle with the sound a little bit more. Let me know if it's still really quiet. It's the heater in my house has been going pretty loud anyway, so there might be some background noise. I apologize for that. Anyway, tonight I want to try, instead of just going through basic how to use Theano to do very simple things like we did last week, we're going to try to use Theano to do sort of what we did in TensorFlow at the beginning, which is going to be classifying these MNIST digits. And we're going to start with this simple logistic regression. So I'm working on some tutorials that are listed on deeplearning.net/tutorial. This looks like a pretty good place to start learning a little more in-depth if you want to do actual machine learning things. And theirs happened to walk through with Theano, so I thought, why don't I do that too? So I've opened up a couple here. I highly doubt I'll get through all these in an hour. There's a good chance I won't get through one of them in an hour. That's just the nature of things. But let's jump right into this classifying MNIST digits using logistic regression. As usual, this is the standard like Python doc page, which I'm a big fan of. Note, the section assumes familiarity with following Theano concepts: shared variables, basic arithmetic ops, t.grad, float x. So t.grad is going to be gradient descent, float x. Let's look at what float x is. Float 64, float 32. Okay, just a certain data type. Basic arithmetic ops, that we did last week. Shared variables, I'm guessing these are like variables in TensorFlow. Also supposed to make the function with internal state. Yep. So there's a good chance our weights are going to be shared variables. Just a guess. We're going to find out here. The code for this section is available here. So if you want to see the actual code, and I might be referring to this to quote-unquote cheat a little bit, that's what I'll be looking at. This deeplearning.net/tutorial/code/logistic_SGD. Probably for stochastic gradient descent, which is how they're actually computing the weights. We'll get into that when we get into that. All right, we're going to show how Theano to be used to implement the most basic classifier, logistic regression. You'll also hear me refer to it as multinomial logit model, because that's just how I happen to learn it. Again, this is the MNIST dataset, so we're classifying pictures of handwritten digits that are 28 by 28 pixels. We're trying to classify them as 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. This originally comes from a US Postal Service problem. And in logistic regression, they're giving you this sort of background. Essentially, we're going to be estimating a set of weights for every digit. So we'll compute, you can sort of think of it as like a score for every digit. And it's going to be like e to this score divided by the sum of all the e to the scores is the probability of that particular digit based on all the pixels that we see. Yes, here are features, the x vectors here, are just the pixel darkness values. These are not black and white, these are grayscale images. The B is just sort of an extra feature that's all ones, indicates a bias. Some digits are more popular than other digits, so they get a bias. In some derivations, the B just gets lumped into the X as another variable. Sometimes it's held separate. I suspect they like to hold it separate here, just so that you don't have to remember to hold the value constant 1, like when you're making the neurons. I don't know, it might just be a preference. It's not really important. So yeah, this is the probability that Y, which is your output digit that you're guessing, or the output that is actually your digit equals I, whatever class, given X, all your features, and the weights, and the bias is this. So they also call it Softmax. And they're just going to do the sort of the silliest thing you can do and say, well, the predicted class is going to be whichever one has the highest probability. Note that you could have one that's at like 40% and another one that's at 38%. Those are pretty similar. And that doesn't leave much percentage left for all the other classes, but the one that's 40% it will say is correct. Oh well. So what are we doing here? They say, here's the code to do this in Theano. Snap your fingers. So we see self.w is in fact making Theano.shared. So this is something that's interior to the neural net. Well, it's not a neural net yet. That's something we're going to estimate and be computing over many iterations. They initialize it with zeros of size number in, number out. Value, numpy.zeros, of that shape. I don't know what n in or n out are just yet. And it's saying these are floats. Its name is w and borrow equals true. I don't know what borrow does. I feel like I looked at that last week. Let's find out. I've got a blank sheet here. Oh, did I lose my Vim session? This is terrible. I've never had this much trouble with Vim before. Absolutely awful. Cron/Theano. Alright. Tab new MNIST. There we go. Did I have borrow here? No, I didn't. Okay, so we don't know what borrow does, but that's okay. Some things we don't have to know. Do they, in their actual code, what do they do? Import Theano, import Theano.tensor. Let's do that. And we'll just import Theano straight up. We installed it last week, so we don't have to do that again. Let's see if this still works. Big money, big money, big money, no whammies, no whammies. Stop! Big money. Fantastic. We can still import Theano. So really, we want to be classifying these weights using all this input data. And we'll probably be iteratively determining those weights using what's called gradient descent. Or stochastic gradient descent, as the case may be. In this case, it's a simple logistic regression, so there's any number of ways you can compute these particular variables. Gradient descent is just very popular in machine learning and neural nets in particular. Right, so you initialize your weights, you initialize the b-values, which is just another weight essentially, and symbolic expression for computing the matrix of class membership probabilities. W is the matrix of column K, represents a separation of hyperplane for class K, also known as t.input is going to end up being our 28 by 28 array of pixel values. Probably here it's going to be condensed down to 28 squared, which is 768, I think. 784. I can't do math. It's alright. That's why I have Python. So 784 dotted with the weights. So you take the first pixel times the first weight, add that to the next pixel times the next weight, and so on and so forth, plus 1 times whatever the bias is. So I might try doing this with a W that's 785 long, and I'll just roll this B value into that, just for fun, just to see the difference. So and what are they're just putting this all in a big honkin' class, right? Yeah, they're making a logistic regression class. So let's try that. If they're gonna do it in a class, we can too. Like normally when I'm just goofing off in Python, I don't necessarily make things a class, but hey, there's nothing that says that we can't do that. So logistic regression class, perform logistic regression using Theano and stochastic gradient descent. Fantastic. So we want our self.w, the weights. This is going to be Theano.shared variable, is it called? Theano.shared is all. And what are n in and n out? Those really ought to be, I would have thought. It's not 28, 28, and 28. But from the scope of this, that's really what it looks like. Oh, initialize dates with its matrix of shape in and out. Yeah, well, duh. This may inform me more. I need a definite input n in. Number of input units, dimension of the space in which the data points lie. Number of output units, dimension of the space in which the labels lie. Yes, duh. So I need 784 inputs and, of course, 10 outputs. Right? Because there's 10 digits. numpy.zeros and in, comma, in, out. What else? That's our numpy.zeros. No. Yes? Values. Right, our value. We're saying, what are we initializing this to? And I like that. Value equals numpy.zeros of this. And dtype I need in here. Yeah. Dtype equals theano.config.floatx, I believe. Yep, that's what they got. What else do we need? We need to say borrow equals true. And we need to give it the proper name. That's right. So you give it an actual name. It's important to have commas between our arguments. Borrow equals true. Is that correct? Yes. And I'm going to include my biases in my weights vector. So I'm not going to worry about it. That may bite me later in an actual neural net computation. But for this, I'm choosing not to worry about it. And then, of course, we need to compute the softmax function. So they call this self.p.y given x, right? Yeah. Equals our tensor t dot neural net dot nnet dot softmax for the multinomial logistic multinomial logit. Blah. This should just be t dot dot t dot nnet dot t dot dot. So we're doing a nice matrix multiply of our whatever our input is. You know what? I'm not going to call it input because that's a reserved word in Python. I think that's dumb. I'm calling it invals now because that makes a whole lot more sense. And W. That should be all I need. I don't need to do plus B. Self.w. These days when you get burned. Yeah. And all this talk about the hyperplane, that's all just really saying this is a linear classifier. So you don't need to get too worked up about that. And then I'm missing a print. Which one is our actual best class? Which digit do we think it actually is? That's going to be t.argmax of this self.py given x. Argmax self.py given x. Right? And what's the argmax? Just t.argmax. And we give it an axis because why not? So the axis tells you along which dimension to consider these things. And this is one of those things that I can never remember in NumPy how it works, and I'm probably Theano follows the same style. All right. So this is all just to, given the values of W, well here we're initializing to zeros, but so to given these W's, compute the softmax of that, the multinomial logit, and then spit out, well not spit out, but compute what do we think the best the best digit is to match these pixels. Okay. Since the parameters of the model must maintain persistent state throughout the training, we allocate shared variables. That's the key. It's shared because it's persistent. This is just like the TensorFlow dot variable. It declares them as being symbolic Theano variables, also initializes their contents. Blah, blah, blah. We compute P of Y given X, W, and B. To get the actual model prediction, we use t.argmax to pull out whatever the biggest probability thing is. Okay. Now, of course, the model we've defined so far does not do anything useful yet. Yes, of course, because the parameters are still in their initial state. Namely, 0 is the initial state. So what do? We need to actually define how we want our parameters to be computed. And one of the ways you do this is by defining the loss function, and you might also see it determined as the cost function. All the same kind of thing. Here, what are they saying? Learning optimal model parameters will always minimize the loss function. Use the negative log likelihood as a loss. This is a standard measure for the multinomial logit regression. You'll see log likelihood all over the place if you study any of these kind of models. That's a standard thing to use that you try to optimize for. So like we're trying to maximize the likelihood that our model is sort of true. Maximizing the likelihood of the data set D under the model parameterized by theta. Yes, that's just what I just said. I swear I'm not just reading the screen and then paraphrasing. I'm thinking of it and then reading and realizing, oh yeah, that's what they said, but not as smart. I wouldn't worry too much about this exact formula right now. Defining the likelihood of L and the loss, lowercase l, this other stuff. Entire books are dedicated to the topic of minimization. Gradient descent by far the simplest method, yes. Yes, and we'll be using stochastic gradient descent for details. So they've got eventually this big mess. Y.shape 0 is symbolically the number of rows in Y, the number of examples. Call it n in the mini batch. So you're going to train your thing with a few images at a time, maybe 10, maybe 100, whatever. You'll sort of compute the error rates for those given your starting parameters, and then you'll use that error to update all of your parameters. So the mini batch is just how many you do at once. It's sort of faster to do like a few and then update your model, and then do a few more and update your model, and so on and so forth. You'll go through all of your images multiple times, but doing it a little bit at a time, you can save a lot of your effort and get a lot of bang for your buck still. T.A range, excuse me. That's, yes, the number of variables that we had, or not number of variables, number of images, make a 0 to n minus 1 array. I don't know, this is like a weird like stream of consciousness. Like this is this, this is this. It's like this could have been broken up on lines. Oh well. T.log self.p of y given x. So that's p of y given x all this stuff. So that's what this is. T.log p of y given x. And we grab a particular set of values out of this. Namely, the first n rows, n being the number of images we pass in at once, and y being, is that all the images? I think that's all the images. Is that what I see here? D, the data set D. And t.mean. So where do they define t.mean here? It's a matrix of log probabilities, call it LP. With one row per example, yada yada, t.mean. Even though the loss is formally defined as a sum over the dataset of individual error terms, in practice we use the mean in the code. This allows the learning rate to be less dependent on the mini batch size. Okay. So, formally speaking, you would take the sum over all of the images that you put in a given mini batch and use that to compute your negative log likelihood, and use that to compute the error rate. But in practice, apparently, we just use the mean of the error, which is probably giving you similar results. I mean, if you have a big outlier, that's still going to affect you. And I guess that's just easier to compute. So this inside thing, you don't see a sum or a for loop here, because it's all doing array operations. and that's defining our loss function, which is not going to go in the init. I am curious. Creating the logistic regression class. We have all the tools we need to define logistic regression class. They didn't actually. I guess we're not implementing stochastic gradient descent. It probably just you get it for free in Theano. Stopping condition is met. Da 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 da. I wouldn't be surprised. Maybe it's not. Maybe you don't. Oh no, MSGD. That's probably what it is. Oh no, Theano.function. We'll find out. We'll find out. Okay. All the tools we need to define logistic regression. I kind of don't like that they're just giving me all the code for free, but it is what it is. So we actually need to compute our, or not compute, declare what our parameters and whatnot are. Those things were kind of already declared, but that's okay. That's what I get for not turning paste on. Set paste. One of these days. One of these days, guys. And we're not using input. Note that how that's highlighted as a keyword. I don't like that. Even though it is input. You can blame Python for that. So this just sort of initializes the class that says, yes, these are all the things that we have. This doesn't actually run anything. Compute the negative log likelihood, which is just this one-liner. So, whoa. Hang on, I think I might be short a open close paren somewhere. Maybe? No? I think we're all good. Alright. I was getting a weird tab indent, but whatever. Okay. Negative log likelihood. That's what they like to call it. That's what they call it. And of course, in Python, you got to pass in self and y. Y being the vector of this. This math doesn't parse well in here, but it does in the actual page. Corresponds to a vector that gives for each example the correct label. Yeah, so y is just the big list of labels that you have. So y is a list of labels. So like what the digits actually were. All right, so and this is us computing the negative log likelihood, all this jazz. There's the probability of y given all our parameters. We take the log of that. We grab what we think are the correct. We grab those classes and all of this data, and we take the mean of that. So I'm not going to include all that stuff back in this class again, since we're just doing that to figure it out. Note that this is sort of feeling a little like we're having to write a little bit more code than I feel like we did with TensorFlow. So that's something that I'm sort of getting the feel for. Errors. So we need to compute our errors, of course. Return a float representing the number of errors in the mini batch. Check if y has the same dimension of y predicted. So if you didn't predict 10 things, or maybe that's not right. The number of dimensions in y. Oh, yeah, if you didn't predict the same number in mini batch and with the same number of digits, if for some reason you're only predicting 1 through 9, you're doing it wrong. That is not the correct way to do that. I don't know why my tab is set to 8. That's really aggravating. Self, y pred, right? No, just y. Maybe it's because I'm in this class, logistic regression. That's why I'm getting this weird thing. So we want to ask is self.ypred end dimension dot endim. Is that the way that works? Yeah. Dot enddimen. So number of dimensions. How multi-dimensional is our multi-dimensional array? If that's not true, we got problems. Like, All right, this is really ticking me off. This 8. That is not normal. Vim set tab width. Set tab to 4 spaces. Sorry, we have to take a detour here to reset my Vim. I don't know why it's being like this. Was it like this last week's? How to make my Vim never use tabs and make the tab key equal 4. When indenting, show existing tabs of 4 spaces width. I'm pressing tab. There we go. I'll just, for the moment, we'll just do this. Ah, wonderful. Okay. If this is not true, that's bad news bears. If our y predicted is not the same number, we can nuke all this Vim stuff for now. Yeah, and they just say raise type error. I'll just copy that. I'm not too worried about that jazz. And that's what I get again for not. There we go. What in the hell? Might tidy this up a little bit. There we go. Much better. This whole thing needs to be here. Much better. That's so good. Okay. If dtype.starts with int, check if y is the correct data type. T.not equal operator trains vector of zeros and ones, where 1 represents. Oh yes, yeah, it really ought to be an integer. Is there a better way to do that? Dtype. Can I just ask if it's? I guess they say like int16, but it could be a uint, right? And like, who cares? An unsigned integer, like that doesn't really matter. Numpy.uint. What if I just say a equals numpy.dtype int64? Is that a thing? A dot char? No. A dot name? A dot names? A dot string? Oh, that ain't right. A dot type. So I don't have a good built-in checking like, is this an integer type field? And they're asking starts with, but I'm gonna say is in. If int is in, is that how it works? Oh my gosh, I don't even freaking remember Python. It's not a string that contains, right? But I can ask ABC in ABCDEF. Yeah. I don't need days, that's the problem. One of these days, man. One of these days. Y.dtype. Yeah, I'm not going to use the starts with because you might have a uint. And what are they saying? Take the mean of the number of times that your prediction is not equal to the actual prediction. So again, we're taking the mean instead of summing up over everything. So that's the same thing. But I'm choosing to just do the Python in. And else freak out. Yeah, if int's not in the YD type, well, I don't know what you're going to do. Not implemented error. Not implemented. Yeah. Need an int data type for predictions. Preds. That's all. That's all that we need. We don't need to get way too specific here. All right, that's our errors. What else we got? We instantiate this class as follows. But all right, how does it know to do stochastic gradient descent? It hasn't done that yet. We're computing the negative log likelihood, sure. We're defining how to compute the errors. Yeah, we're gonna make this matrix X of the data. We're gonna make this matrix Y of the Y vectors. It's not a problem at all. All right, let's just do that. Data is presented as rasterized images. That's the MNIST data set. So this is outside of the whole class business. T.matrix x, right? That I can do, yeah. Y equals T.array, T.I vector, a vector of integers. Y. Yep, that's all we got. And then what do they call it? They call it model classifier. Equals logistic regression. Our invals are simply x. Yeah. Our number of ins is equal to 28 times 28. I happen to notice based on the MNIST data set, plus 1 for the bias vector. We'll have to add that in later. And our number out is 10. There's 10 digits. So let's define all. Oh, let's turn off auto indentation first. Ding! I didn't like that. Didn't like that one bit. What's the problem here? Inconsistent use of tabs and spaces in indentation. Not surprising. Not surprising. What doesn't it like here? Oh. Why? These are not actual. My tabs are not actually spaces. There we go. Let me fix that. Let me go back to that Vim. Vim turn tab to space. Converting tabs to spaces. Vim tips wiki. Redefine tab as 4 spaces. Set expand tab. Okay. I don't know. Maybe it's not reading my vimrc. Maybe that's the problem right now. Okay. I think we're all good now. Hey, what do you know? It all works. Does that work? It has no attribute B. Of course it doesn't have an attribute B. I'm rolling that all up in some other jazz. But I will put my parameters right there. Like a good soldier there. Okay. That's our classifier. All right, we're halfway through. We're almost there. We're making good progress. Cost. Okay, so we're going to end up saying this is our classifier class. This is our cost function. Or this is our actual cost, and then we're going to use this Theano gradient descent to do that directly. So let's do that. Again, this is all just sort of like compiling what the code is supposed to do, right? This sort of defines what the model is. Hang on. This defines what the model is. This defines the cost function or the score, what we're climbing on. Learning the model to implement MGSD. It's multiple stochastic gradient descent. Most programming language want to start by manually deriving the expressions for the gradient. We're not going to be doing any of that. Because Theano does automatic differentiation. So that's super convenient. We only need to worry about this W one. Why do they call it G for the gradient? W. So given that the cost is this and the classifier is this, compute what the gradient should be. And then we update. I'm kind of surprised the update didn't go inside the class definition. Actually, what is this? Getting started? No, not that. Does it? Errors. No, it doesn't. Huh, funny. Go figure. So we're just going to update W. So we're going to say this is the old W. This is the new W. Whatever our learning rate is, who knows? Updates equals classifier.w, comma, classifier.w minus learning rates times GW? Yeah. Times that grad. However wrong we felt like we were. So this says, compute how wrong we were in a way. And then the learning rate says, all right, let's take some fraction of that and fix up our W a little bit, recompute, see if we get closer. All right, now we're going to make a Theano function. Remember we did this last week, usually in a lot of like simple basic arithmetic. Our input is going to be this thing called index. I guess that's going to be an I value. Index times batch size. Oh, that just says which one of our like mini batches we're doing right now. So that's going to be some value 0 through however many batches we have, maybe 100 or something. And this is just how they're computing which one they run. So they're taking this chunk, the ith chunk, which is batch size long. So it's going to start at 0 times batch size, which doesn't matter what batch size is, that'll be 0. And then it'll be 0 plus 1, it'll be 1 times batch size. So they'll grab the first batch size guys of the x's, which are pixel values, and the y's, which are actual digits. Updates, so after every step, it will update that according to updates. So this is just a special format for the updates, I guess. The outputs are the cost, which is interesting. That returns the cost, but in the same time updates parameter. All right. Like I guess in the trained model case, we don't actually care what the output is. We're going to get the output later. Huh. All right. Let's see if we can, how much of that I can remember. I could just copy paste, yes. But we want to remember how to use Theano.function, actually. You know what, I'm going to leave Theano.function on there right now. So we got to have our input, right? Inputs equals, we're just going to have an index, it's going to be some number, I. Our outputs is going to be this thing cost. Again, just this. Our negative log likelihood, sort of our score. Our updates, things that we're going to change after every iteration, after every mini batch that we do. That is just going to be updates. Updates equals updates? Yeah, whatever. And givens, which is basically what we're putting in. What we're putting into the model, which is a dictionary, I believe. Yeah. Of x. So we've got this thing x here, and we put that into this logistic regression. And what is that actually? Oh, that's which particular set we're working with. Which mini batch. Train set x of I times. I'm just going to use I. I don't want to type out index every time. I is a standard index. Batch size to I plus 1 times batch size. Make sure you use those parentheses there, or you will get burned and you're going to have a real bad day. Ugh, misery. Alright, fine. We'll do that. And y, of course, is basically the same thing. Straight set y. That's all. Close off the dictionary. So this is how we're actually going to build our model. We sort of defined how the interior works, connected those pieces to things that Theano wants. Like, we didn't have to compute the cost as a separate variable over here. I don't think so, anyway. Because this is all symbolic anyway, so who cares? Maybe that's something we'll fiddle with. The actual gradient, again, just a symbol. Say t.grad of the cost with respect to WRT, the classifier W, which is, as I say, our weights. Because it's going to do the automatic differentiation, which is very convenient. Okay. Updates as a list of pairs, yada yada. Yes, these pairs, the old value, and the new value. Or the thing you want to update and what its new value is, I should say. Which is sort of like a dictionary. And we're returning the cost. On every function call, replace x and y with the slices from the training set specified by index. Evaluate the cost associated with the mini-mass. Okay, testing the model. As explained in learning a classifier, when testing the model, so that's computing the errors here. So this tells us, on average, how many do we get wrong? Interesting. Oh, yeah, this tells us our percentage wrong. Yeah, t dot not equal. Yep. And we're taking the mean of a bunch of zeros and ones, so we're going to get some number like 0.1 or 0.2 or something, hopefully. Then create a function test model and a function validate model, which we call to retrieve this value. Oh, so test model just says, put in our index, see how bad our errors are. Validate model says the same thing, but it uses the validation data set instead of the testing data set. And it'll note that these are both different from the training data set. The only difference between them is the test model draws as many batches from the testing set, the validate model draws it from the validation set. Validate models are key to our early stopping implementation. These functions take a mini batch. All right, so we'll get into that. We've got two sort of separate tests going on here that are doing essentially the same thing. Let's whip those up. I'm going to copy this because it's very similar. I'm going to finish writing that function first. There we go. There we go. Much better. Not train model, now test model. Our inputs are still I. Our outputs, however, are now classifier dot errors of y, right? Yes. And instead of train, we have test. Instead of train, we have validate. So what they use? Validate, valid. Good. I like a little shorter. Outputs are classify. Don't need to type outputs again. Classifier dot errors of y. There we go. I don't need updates in these, right? No, we're not updating anything. This is just testing things. Before I get burned, let me change this to valid model. Groovy. Let me throw some white space in just to stay sane. And let's just run this stuff. Right, learning rate isn't defined yet. That's an important note. Let's define learning rate. I'm just going to arbitrarily choose 0.01 right now. I haven't yet seen things that give good suggestions on what the learning rate should be. So that's something that I'll be curious to read more about. I is not defined. That is a real good point. I is not defined. I is supposed to just be a, they call it index. Index. T.L scalar. So T.long scalar. So an integer. So let's grab that. We can just put that right here, that's fine. Of course I lose everything, that's just the I. This is which mini batch we're on. Validated, right? We don't have our data set, so we can't actually build those particular, we can't run those, we don't have the right symbolic variables defined just yet. Putting it all together then. So what do we want to do? I need to load in the data. That's one. I haven't done that yet. That's an important thing to do. Then we're going to run this train model a bunch of times. We're going to run test. We're going to see how bad we did, and then maybe we'll fiddle with our model a little bit. Then we'll train it again. Then we'll run test, and maybe it's okay. So then we run it on validate, and then we say, okay, yes, it's definitely, then we're pretty sure it's okay. The key is like you hold back that validation data until the very end. You're willing to train your data on, train your model on all this data, and then like every now and then you test it on test data. But this is to make sure you're not overfitting the training. But if you test that against your test data all the time, then you might just overfit on your training plus your test. So that validation, I'm pretty sure, is going to be until the very end. And normally that's like a hidden thing you can't see. If you're competing on Kaggle, like they have a validation data set maybe separate from what you have. All right. So what are they doing? They're doing all this pickle stuff. They've got the class to open it, yada, yada, yada. Load data. This is somewhere where I'm choosing to just copy what they have. I don't want to have to think too hard about loading the data set. That shouldn't be something that you fight with. Like, it actually is. Loading the data set is non-trivial in a lot of cases. And of course, here we go. Let's copy that. Copy that, Roger back with another thing. Sorry, sometimes I randomly like break into song lyrics that I'm familiar with. I think it's just a human problem. All right, where did I grab? I grabbed everything before shared data set. And shared data set is part of... Yeah, shared data set is part of that, which is a little weird to me, but that's fine. Nothing wrong with that. I'm going to remove some extraneous white space. So this is defining a function inside of another function, which there's some good times you want to do that. It can be a little slow, but we're not too worried about it. I don't want to worry about this. This basically says we're grabbing MNIST. Package, we're going to need to URL lib. I'm going to need all this crap that they start their file with. All the imports that they do, I'm going to need a lot of those. Basically all of these. I probably don't actually need sys and time it, but that's all right. We'll throw those on there. We're just learning. It's okay. It's not the end of the world. I don't need all these comments. Comments are great. I support more comments. They have good coding style and everything, but I want to make things just a little bit easier to read what the hell I'm doing. And that's okay. Now we're looking a little better. All right, let me try to, something called, yeah, they've got some Python 2 stuff. Let's do that, and there we go. Any other prints? No other prints. The prints is not here. Okay. All right, 12 minutes. Let's see if I can get this basic thing working. We already have our class Logistic. We don't need that. They have a load data. I have a load data. I stole it. We just need to load in our data sets. There we go. No, copyright. I'm not going to be making a function for it. I just want to do it locally because I'm a horrible person. All right, data set is not defined. Load data set. Oh, mnis.pickle.gz. That's our data set. Pickle.gz. There we go. AIMOS is not defined, isn't it? Oh, I didn't actually import those things. File is not defined. Why would you do this? This is what I get for not actually checking the... Right, file is not defined because I'm not actually writing a /. Not portable at all. That's okay. URL lib has no attribute URL retrieve. Interesting. I wonder if this is a like Python 2 versus 3. URL lib dot. URL lib is not defined. Import URL lib. URL lib dot request. Extensible library open URLs and variety of protocols, yada yada yada. .url. Okay, so we're just missing, and I just crashed. No, I didn't. Just kidding. Okay, so we just got to fix up a couple things that are probably just Python 2 like. So we're gonna put request in here. That should be it. There's no other print statements. There's none of this other jazz. They import URL lib in here, which is fine. If data dir equals. Oh gosh. Let's do this again. File not found. Okay, that's real good. What if I just don't pass it in anything? I just want to download the file. Can you work with me? What if I do this? Test set is not defined. Okay. Here's what I want to have happen. If not this thing. Look, I want this. I don't care about this jazz. This is what I want. Right? Yeah. I just want to go grab this and download it. That's what I want to have happen. MNIST.pickle.gz. That is what. /. That's what we're going to call it. Oh, there we go. I didn't actually reload load data. I just used the proper format for it. So it's grabbing that data. I could probably have stolen it from TensorFlow, but whatever. That doesn't matter. This is taking its good sweet time here. How big is this data? Did they tell me that here? They don't. That's okay. We've got our index determined, we got our X, we got our Y, we got our classifier, we got our cost. Then we can define test model and all this other jazz. This stuff. Let's move this down here. Because now we've actually defined test set, train set, and validation set. And by defined, I mean we still have to actually define those. As in x comma train set y equals data sets 0. And we're going to say train sub and test. We say train sub and valid. That's the first one. That's the second one. There's that one. Right. So we're loading all this data into this data sets object. And, oh, what the hell? Can't catch a break around here. Test set is not defined. I think I'm okay with that. Oh, shared data set test set. Right. I clearly did that wrong. That should have been obvious from the get-go. Load data. Interesting, interesting. Load data, load data, load data. cpickle.load f. Does this not happen? Did I miss that part? That would be pretty miserable if I missed that part. I'd feel really dumb. I think I did miss that part. I got all this, and I forgot to actually load it. Bad copy paste, bad copy paste. Let's do that. cpickle is not defined. That's because cpickle is just known as pickle these days. Another fun fact. Okay, almost there. Almost there. Things are never as easy as they're meant to be. ASCII codec can't decode this byte. Of course it can't. Of course it can't. So this is another Python 2 versus Python 3 problem. Pickle.load, not load s. No. Can I say byte 0x90 in position 614. Ordinal not in range 128. No, it's not, isn't it? Unpickler, so how can I cheat and tell Pickle to use default to ASCII and strict respectively? Coding can be bytes. Alright, so during our Pickle, we're going to tell it to read it as bytes because we don't care. And we'll hope that the rest of this goes okay based on that. So we're Pickle, we're in Python 3, we need to give it an encoding. Encoding equals bytes. Let us see what happens then when we redo this. There might be a Python 3 version of this particular tutorial. That would have been good to see. NumPy is not defined. You gotta be shitting me. Oh my gosh. NumPy. One of these days, man. One of these days. At least that means it's working. Right? It didn't get that far before. And it had downloaded the data, and the data's already downloaded. Okay. A few minutes left. Boom. Train that. Now we're ready to find our models. Go. Oh, it didn't work. I don't have a batch size. What's the batch size? What do they use? Oh no. Probably 100. They 600. Okay, fine, 600. Batch size equals 600. Go. Oh, my data sets are a little warped here, aren't they? Train set X. Tensor type, float 64 matrix, dot ndim or something? I just want length of train set X. No. That shape? Yeah, that's real cute. Not helpful. Subtensor. Oh, that's cute. Real cute. Because I wanted to just throw the bias in there in its own right. Right. But is that going to happen? Is that going to happen now? How big is A? Has no length. Of course it doesn't. Type, round, shape. Shape? God, seriously? A.ndim. 1. Right. A of 0. A of 1. A of 784. Alright, so that just doesn't work. A.flen? No. Right, so I wanted to append my biased units directly to this. But it is seeming like it doesn't want to let me do that, which is kind of frustrating. Train set X. Tensor type, float 64, matrix, dot eval. No, I mean, this should contain the actual data, right? I'm not crazy. It's like, I just want to see the data to verify I'm not crazy. They've got all this other jazz, prediction using the trained model. We might have to continue this at another time, which would be really unfortunate. Train set X, dot get value. See, like, this is the goofiest thing. This. Why? Dot get value, borrow equals true shape. What a pain in the butt, I tell you. And train batches. Yeah. So if I say this, yes, so I have 50,000 things of size 784. That is the information I needed. Thank you. There's my actual goddamn matrix. What a headache. What a headache. So 50,000 rows, 784 columns. If I say numpy.concat that, and I say numpy.ones. Ho ho. 50,000. Does that do the right thing? Concatenate. Only length one arrays can be converted to Python scalars. Dot transpose. Let's try that. No. So this was me trying to add a one long guy there. How do I train set X? So Theano tensor type concatenate. We're gonna try this. We're gonna extend a few minutes here to see if we can do this. Basic tensor functionality. You think I would have learned this? Concatenate. Theano.tensor.concatenate. Hey, it figures. But like, I don't want this to be a. Is this a Theano tensor type? I guess it is. So train set X. Is this Theano.t? Yeah, so t.concatenate. My tensor list is this, comma, numpy.ones. And what is our magic? I'm going to say n images equals train set X dot get value borrow equals true. Of course, that makes the most sense. Dot shape 0. Yeah, there we go. And number of train images, of course. Is that a thing? Yes, perfect. Numpy.ones and train images. Alright, let's see what happens here. Join tensors with the same number of dimensions. Really? That doesn't make sense. Well, they have the same. They both have 2 dimensions, right? Train set X dot ndim. Yeah. Well. It's got 2 dimensions if it's a one-dimensional array, guys. Ah, man. So really, I have to do this silly business where it's this many rows and 1 column. Cool. Thanks, Arda. Thanks for adding me to your list of awesome YouTube channels. I'll let you know if I see a bump. And I'm glad you find this entertaining at the very least, to see me continue to screw up the most basic operations. Data type not understood. Oh, you're breaking my balls down. Maybe the problem is I should use t.ones. Data type not understood. T.ones is a thing though, right? Because this should just be a list. Join.0. What does that mean? I don't know. Let's say train set X equals. Can I do that? Train set X dot get value dot shape. Tensor variable doesn't have this useful information for me. What if I numpy dot concatenate? 0-dimensional arrays cannot be concatenated. 0-dimensional arrays cannot be concatenated. All this because I didn't want to put in a bias parameter. So maybe I should just put in the bias parameter and admit the error of my ways. All right, fine. I'll put in the stupid bias parameter. Ugh. I wanted to just have pure, nice linear algebra, but I can't have nice things here. Nope. be, this is going to be, how many inputs does this have? 1, right? Oh gosh. RB has, oh, I guess vector of n outs, n out zeros. All right, well that's fine. RB.0 is n out. N out, comma, like that. Plus self.b, right? Yep. All right, but that should be about the only other thing I need here. I need to update B, just like I update these other guys. I need a G of B now. Look at this. Ugh. Okay. Now we're going to find out what things I forgot to include for B. That means I got to redefine all this garbage. Oh my gosh, oh my gosh. What a headache. Do our learning rate, all that stuff. Do all this. I don't need to load the data again, I did that. We'll do that, okay. Okay. Doing things, making the training data set. It's compiling the Theano code, so that's going to take a little while. All right, this is where I should have been 15 minutes ago if I hadn't been trying to get away with that bias without a bias parameter on its own. Shouldn't be that hard. It really shouldn't be. And of course, if just something takes me more than 5 minutes in the stream, I feel like it's taking forever. So there's this built-in impatience in the model. What are they doing? What are they doing? Build actual model. That's a key component here. They compute. They're doing all this epics business. Where did they compute how many batches that they had? Here we go. This I'm going to steal because I already understood this. Right. This is how you get the size, how many images we have divided by the batch size. This should be nominally correct. Drive that back. And then we got all the update stuff. Patience equals 5,000. Look at this many examples regardless. I'm not too worried about that. 4 mini backs. We're not going to be using X range. Try in range. Let's just run in num epics. How many times we're going to go through all the data is considered the epics. I just want to say 5 for now. Because as you get better and better, you'll want to look at the data again and say, all right, well, I did this mini batch and then this mini batch and this. So like, now that I fixed everything, go back to the beginning and say, okay, what was really right? I don't know off the top of my head if it makes sense to always use the same mini batches or if it would make more sense to mix up your mini batches. That could cause problems or it could be super good. Train batches. And what is the magic? We want a train model, right? This is just has given inputs. This cost equals this, right? I mean, that's basically what we're doing. They're doing a lot of stuff here. Iter. I don't know why they're doing that. Oh, because they're considering the epic and all this other stuff. Mini batch average cost. They're computing the validation. Do they validate on every step? And then at the end they run the test? I'm not trying to get that specific here. I just want to run it for a little while and see what happens. Also, we're just going to give ourselves a little bit of I, mod 10, mod 100. 0, mod 100. Every 100th guy, I just want to print what we're up to. Just so we don't go crazy. Will that actually run it? That will run our train model. That should just work for a little bit. And then like afterwards we can actually try to compute what we're doing correctly. Let's just see what happens. Invalid syntax. Right, I don't want to assign that. I want to check that. Guys gotta keep me honest here, come on. Float object cannot be represented as an integer. For I in range n-trained batches. I'm in Python 2 now, or Python 3, I should have known. I wanted integer divide. All these nice things. I like Python 3, but there's definitely some things that get on my nerves. What did I miss that I need to throw in here? Minibat, the index number, of course. Derp. Hint, rerunning with most Theano optimization disabled. Not shown, not shown. Apply node caused the error. Okay, well that's new. Has but it's okay. No, this is easy to fix. I forgot to remove the number of my bias parameter as an extra parameter right here when I make instantiate classifier. That's easy to fix. Redo everything. Hey, there it goes. What do you know? Boom, 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 boom. I thought I would have had more in the I there. What is this cost? Array. Something, 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 something. Okay, and if I test model array, and that's weird. Right, let's real quick. Prediction using a trained model. Let me just steal their prediction code just to see. Again, this isn't even using a neural net just yet. Ooh, that's not what I want. We're not using cpickle, and I'm not loading the saved model. No, we ain't doing that. I'm just using the pre-existing classifier. Return predicted values. Print predicted values. Predicted values. Does that make sense? Oh, I need this too. There we go. Do that, and that, and there we go. It's gonna load the data set in again, and that's all grand. So if I say predict has no attribute input, that's of course it doesn't. Inputs classifier dot invals, because I don't like to call things input. Call me crazy. One. That doesn't seem right. For the first 10 examples in the test set. Somehow I doubt they're all actually 1, so I suspect we've got a problem somewhere. So we may come back to this next week. We may not. There's clearly some issues to be worked out here. Part of it is that I'm trying to go through it quickly. Part of it is just differences between Python 2 and Python 3. But I strongly doubt that all of the values. And then again, maybe it's possible that all those first digits are 1s. So, actually, one move. Let me do this. predict model. What is predict model supposed to be? And that's our function. Test set x of the last 10. If the digits come in order, then I'm not crazy. All right, now. Nope, this is wrong. To be determined what happened, where we went wrong. This is part of what I get for not just copying the code, but hopefully we learned a little bit more about what was going on. And when you have proper time, you can go through and work out all those bugs. But until then, I think I'm just going to have to call that. All right, so that is all we got tonight, but I'll be back next week, hopefully with more of this stuff or more of something more interesting. I promise we will get to neural networks with Theano at some point. Once this is working, hopefully expanding that should be even easier.